It's an in-memory key value store. It supports all the commands which Redis 7.2 had. It supports lots of cool data structures. So like hashes, sets, sorted sets, streams, pub/sub, you name it, we have it all. So in order to understand how different memory efficiency changes have been introduced, I'll briefly touch upon the two different operational modes. The first one being standalone. This is how valkey was created, where there is a primary node which has all the key space and all of the data gets replicated to its set of replicas. And the other being is like there is a certain scale which you can reach with vertical scaling, and beyond that, it's not able to fit any more data. So there's a horizontal scaling approach where there are multiple primary nodes, each with its own set of replicas. Each primary would be owning a set of slots under which there will be multiple keys. So that's the design approach which valkey has taken to provide more scaling. So let's briefly touch upon how internally valkey stores data. At the core of valkey, there is this hash table implementation. It is pretty generic. It supports like any kind of key value pairs. And the basic idea is that there are buckets, which you can see in the diagram. So there are multiple buckets. You receive a key, it gets hashed to a particular bucket. And there is this dict entry, which is like a holding layer for the key value. And like you see, there's a next pointer because we have chaining to support multiple key collisions. Overall, this structure uses kind of like 24 bytes overall for each of these pointer, key pointer, value pointer, and next pointer. And the design remains the same for both standalone and cluster mode. I'll just talk about the how things goes behind the scene when you send a command to valkey. So a client sends set foo bar to valkey, and what happens behind the scene is we will receive the commands, we'll process it, we'll break it into key value and what was the command type. Once we have the key, we'll calculate a hash of the key. So let's say in this case, it gets hashed to 2. So now we have which bucket to insert the value into. And then we create a dict entry like we talked about. And just for simplification, I've removed the pointers, but the key and the value, all of it is stored in a separate memory address for foo and bar. And over here, we can see that the next pointer is null because there is no other entry. If there is another entry which would show up, then we would do a chaining of it. The crux of the design remains the same with cluster mode as well. But like I mentioned, we need to have this slot to key mapping in the dictionary. So what we do is we have this giant dictionary on which the key value of different slots are still inserted. But there are certain things which we need to support in cluster mode, which is like cluster get keys in slot. This helps us in getting all the keys for a given slot to be able to support slot migration kind of things where you move one slot from a source node to target node. So for that, what we do is we have this slot previous and slot next pointer. So these are the two pointers which we use to establish linking between the keys for a given slot. So you can see in this diagram that there is this key value next, like we saw in standalone approach, but then there is also slot previous and slot next. Over here, I have listed out what could be the key hash be. So the key hash is like foo being 0, baz being 0, bar being 2. So this is for the dictionary. So you can see they come out of the 0th bucket and the second bucket, respectively. However, there's also a slot hash which we compute. This is CRC16 mod 16,384. And that could be, so now that could also be same for different keys. So foo is 10, bar is 10. So in this diagram, you could see, even though they belong to a separate bucket, they are being linked together through this slot next pointer. This is key in understanding how we'll apply the memory efficiency changes in cluster mode. So overall, the idea is to reduce the memory overhead per key so that you could store more keys in the same amount of memory and giving users basically more storage space. And also, along with that change, we don't want any kind of regression in throughput or any kind of behavior changes in eviction, expiration. You get the same experience as is with the memory efficiency changes. So that was the goal of the work we have done. So we came up with two different optimizations. The first one is primarily for cluster mode. What we decided is that we don't want to maintain those two additional pointer overhead from coming from slot previous and slot next. Rather, we could have a independent dictionary per slot to be able to segregate data across slot into different dictionaries. So like the command cluster get keys in slot now can retrieve the dictionary which holds the data for a given slot and get all the keys when you traverse over it. This eliminates the fixed overhead per key, which was 16 bytes. And rather, we were able to solve it with 1 MB of overhead per node, which is pretty low when you see multiple millions of or billions of keys. The only thing which needs to be done in terms of throughput uh, effective manner was that you need to compute which dictionary has the key for a given slot. So finding the dictionary was an additional cost we had to pay. But because we calculate the slot multiple times throughout the command processing, we're able to cache it. So in this diagram, if you recollect from the previous diagram, foo and bar were linked through the pointer slot next. Now they don't need to be linked. Rather, they lie independently in the given dictionary for that slot. So slot S1 would have two keys, foo and bar, and slot S2 would have just the baz. Continuing on that, like I mentioned, we save this additional 16 bytes per key. It also enables for multiple use cases, just not just the memory efficiency. Rather, we could do more things on top of these individual dictionaries now. So let's say after slot migration, you have moved all the keys from the source to the target. Now you need to clean up the source. You could do this in async manner, and it doesn't need to block any of the operations on the source side. I think this is still in proposal mode, but feel free to contribute this change. Um, the other aspect which has shown as good outcome is that rehashing for the entire big dictionary which used to exist in 7.2 would need to move all the keys when the dictionary needs to be expanded. With this change, what happens is your hot slots would expand on their own. So it doesn't need to copy through all of the data set which exists in the entire node. Only the slots which are going through these changes will be impacted. And like I mentioned, this change is only applicable to cluster mode because the slot to key mapping doesn't need to exist in the standalone mode. Moving to the next optimization. This optimization is focused on both standalone and cluster mode. The key observation which we had is, like you see in the diagram on the left side, is that when you get the bucket, we have these multiple pointers to store the key value next. The key is something which is immutable and has the same life cycle as the dict entry. So what we decided is the key being always generally smaller in size and also has the same life cycle as dict entry. What we could do is we could embed it within the dict entry itself. So in the next diagram, as you see, value and next still remains as a pointer, but foo is embedded inside the dict entry. What this enables is to get rid of an additional pointer that is 8 bytes. We have some additional metadata for like 1 byte to figure out where the key string starts, but that gets amortized. And because of the embedding, we also saw some cache inline performance getting better and saw throughput improvements of 1 to 2%. And like I mentioned, this is applicable for both standalone and cluster mode. I'll talk a bit about the numbers which we observed. So I took a use case of keys and value size of 16 bytes. This is like small key value pairs. And I added like roughly 6.3 millions through valkey benchmark to valkey 7.2 node. And what happened is like I was able to add a sync to a Valkey 8.0 node, and the observation was the memory utilization in Valkey 7.2 was 693 MB, and in 8.0 the same set of data becomes 550 MB. This is with both the optimizations, we save around 20% for these small key value pairs. And for me, the best part is like you don't need to make any configuration change, anything of any sort to get this benefits. Rather, you just do a upgrade and it seamlessly shows up, like you get all the benefits. Just to touch upon what are the future things coming up in Valkey 8.1, there is a new hash table design implementation going on in Valkey right now, and that would have additional memory savings. So over the time, you should see much more memory efficiency changes coming in. We are trying to apply that same technology which we are trying to build, like for the key dictionary, for the main and expiry dictionary, into other spaces like shorted sets and hashes. Overall, this should give better performance as Valkey 8.1 and 9.0 launch happens. So feel free to check out the pull request, as well as there are more open issues right now people are working on. Finally, I would like to thank Vitali, who started this, Roshan and Madeline from AWS, as well as there are a lot of help from the different maintainers in the group to ship all of this. Thank you. Any questions?
So I think right now we don't have like a scan slot functionality, right? It's only get keys and slot. Is there any limitations for why we don't have like a scan slot?
From what I recollect, there's the API. So there is an issue where we have discussed like if we can support it, but I think the key contention is like how should the API look like so that everyone can seamlessly benefit out of it. But I think Madeline was the who initially created the issue.
Strong opinions about it. I don't like it, but
You think it's bad? You want to call it extra?
but we're probably gonna do it. Me and Victor, one of the other engineers were talking about we should probably do it. The thing that I don't like is the you don't want, like, from the client perspective, the whole key space should be flat. Scan slot pierces that, and you actually know that there's slots behind the scenes.
Yeah. So I guess from an operator perspective, you want to see the keys in the slot so that like if I wanted to do a really advanced like algorithm, I could scan the slot, and then I can on each key like determine, like some kind of weight and then decide, okay, like this specific one is very high or whatever, right?
Well, if you're curious about heap of slots, there is the slot stats stuff. So we have that. So the decision about the scan slot is I believe we're going to come out with a scan that you can do a flat scan across the whole cluster. And that will keep the facade that there's no slots, or you can specifically say, I want to scan this specific slot, and it'll return a cursor that just scans that slot.
So it'd be like a subset of this.
I think there's no technical challenge as such, but there is this API, how we should expose it to the end user. Yeah.
It seems like it was feasible even before. Right?
Yeah.
But I guess the cursors are kind of hard.
Yeah. I would challenge the there are a lot.
Where? From an end user application developer, where is this?
Want to do a transaction.
The guarantee is same keys, right? So you're supposed to use a hashtag.
On multiple keys.
You're supposed to use a hashtag.
Right. Ergo, the slots are visible.
No, they're not visible, because a hashtag basically says this is the piece of information and these two are co-located.
But you're forcing me to partition my data.
Based on a single unique identifier. You're saying these two pieces of information will be laid out.
Right. So I have to partition my data so that I understand there's groupings of the data.
That's correct, but that's not based on the slot. That's based on I have a tag, and all this information goes together with the tag.
There's already a command get keys and slot ID.
Yeah, we're aware of that, but it's not really intended for application development. It's intended more for slot migration.
It's not like you can't scan it, right? Like it just gives you some number of keys.
It give you all the keys in that slot.
But you can't just dump. You have to pay for it.
Yeah.
It's not going to be okay with scan keys in slot tag.
Well, yes.
I think. Yeah, the other thing with the hashtags that's really hard for end users is like, if you have a hashtag that is big, right? Like you just have like an application that's very heavy on like multi-get, multi-sets, you can end up with a really big hashtag. And then you need to start managing, partitioning that hashtag, and then sectioning off your FBS M sets into multiple different queries that get aggregated, and then you're kind of playing the fan in, fan out game, right? So that's another way where the hashtags kind of fall short.
But what would be the alternative then, right? If you want the data to stay together, then unless you supply a bigger machine. If you want to distribute it to across machine, then you just scatter together or some protocol around it. Otherwise, you just use the biggest machine. Like I feel like the hashtags would, maybe provide more control with custom hashing where you can control where the hashtag is going. Like there are two hashtags, both are hot, and they can arbitrarily get mapped to the same slot, which is the problem. Now they will always stay together. But I know that they are hot, can I move it separately? Like if I wanted advanced controls over that, then it would be like a custom hashing thing where I can decide what slot it gets mapped to. And maybe that's slot exposure, I don't know.
I remember filing an issue sometime back regarding custom hashing algorithm, but I think it's quite difficult to get the experience right as well around that.
Yeah, and it's very much advanced, like you need to know the ins and
Yeah.
outs, but
You have to recognize that things are gonna get partitioned.
and at that time you very well know the slot.
Sort of, once you start that, it just permeates everything.
Maybe another issue is the client side. So a lot of times, like especially for cross slot commands, it'll just partition into 16,000 commands, right? But you could do some coalescing there to like just have one per card, right? Or potentially, right? There's no limitation. I mean, there's a protocol limitation in that you don't allow the cross slot, but if you allow some form of cross slot, then as long as it's all on the same shard, then the client side can then decide, I only need to do 5 requests because all my they're on 5 shards versus like 16,000 requests, which I've seen overwhelm some customer applications.
Yes, Snap has been advocating for that for a while.
Cool. All right. Yeah. No. You want?
Yeah. So basically we talked about the standalone and the cluster mode. Standalone does not have this requirement of slot and key mappings. But I guess from the code-based simplicity perspective, why not use the cluster approach, which is like slots internally, even for standalone case. It's just that all the slots are hosted on the same machine to allow transactions across slots as well. So do we see a challenge in going with that route? Maybe in the future it can pave a path to migration where you're running with standalone. You can make some changes or whatever without doing the bounce on the binary, and then to a cluster mode where now you can start splitting up slots to other machines.
I don't think that is a key limitation for migration though. Like splitting it into slot over the fly, like while data transfer is happening, should be still possible. Like the layout in the standalone mode, I'm not sure, but doesn't hamper us from going from standalone to cluster mode.
And I mean, it kills the branch as well, right? Like currently it's like they go this route or that route, which is like one giant dictionary versus 16,000 dictionaries. But I was just wondering, like, should we unify them over time?
So in code perspective, it's still the same code for both the standalone and cluster mode. It's just that it uses just one index in the key. So we have named it as KV store.
Yeah.
So it uses only one index of it.
Yeah, right now I think it needs a process bounce, right? Like from a migrations perspective, from one giant dictionary to multiple slot, because you have to kind of segment the key.
Oh, you mean in a running node itself, if you want to migrate? Yeah.
Right.
We would have to revisit that. Like I was thinking, like you take a +1 node and do a copy somehow from this node to
Yeah, I
other.
mean, you could build that where you somehow figure out what belongs to slot and something. But is there a reason? Like, does it give us any today, like to keep them at like 4 basic standard?
I think the push, at least from what I hear from people near me, is to go towards cluster mode because it has much better scalability, like horizontal scalability, and like it is more mature as well at this point. So, but it has a long history of standalone mode being there for quite some time. So people have already used that a lot. But I agree that if there is only one mode of operation, it would be much simpler for everyone, like the client developers, the maintainers, the application developers as well. If the TSC members have any opinion on this, feel free to share as well. I see
I mean, you
Madeline is
still
here.
want to, I guess, retain the standalone transactional support because it's simple. You know that all your data is there, so you can put transactions across any keys, right? Now we are saying that artificially you put a hashtag on all of your keys. You want to get it.
Yeah, there's that limitation. And I think, I guess that's a Snap thing, right? They wanted multi-slot operations within multi-exec.
I think that is more of a protocol optimization, like not do the span out when you're going through the same.
Right now, we even don't allow multi-slot operation in a given node, even if all the slots belong to that node,
Yeah,
which,
that's just a gentle nudge to make sure, like, clients, like application developers aren't supposed to be thinking about like making sure everything's co-located.
right.
Like, you're only supposed to be offering.
Hmm.
But I think standalone mode is their intent that everything is co-located.
The standalone, everything is, it's a platform.
Yeah.
Yeah, right.
But there's a lot of people that do their own client running standalone, and it's.
You could still expose it without like breaking the facade of the flat dictionary, right? If you just make the customer go to every node with the whole get or whatever, and then each one chunks it, and then it still would be probably more efficient than 16,000 calls, but you know, they might not. I don't know.
Yeah, some of the other TSC folks, especially I think the Jao and then think the better idea is to have a proxy on that logic. So the end client still you see the standalone, which can do fan out. But underneath the hood, everything can be customized with the proxy. The proxy handles that. So it still looks like a flat key space from there.
Yeah, that's alternate.
Yeah. But I mean, if you're doing an MDAT, you're presumably catching up. So. Right.
Yeah, I guess if you're doing the proxy, though, it's like, why not just cut out the middleman? Like the customer application should know the small assignments, right? But should have a knowledgeable view of how to chart it, right? So, like having a proxy was mode that does the scope.
Yeah, that gets into the whole conversation we've had for a long time at client side. And
Yeah,
they don't do this correctly. So if we could put a proxy, we can find something smart. Why should maybe solve that?
I think individual clients are great. Clients at large.
Yes, clients at large.
Cool. Thank you, everyone.
So I think food is still coming out. So as that gets ready. But I think we want to probably do a break for food before starting the next presentation. So feel free to converse to the release.
All right.
Okay. Well, I appreciate the applause. I hope you can still applaud when we're done. So we were just a minute ago trying to remember when the previous meetup was, because we had talked about the status of the work that we've been doing on the vector search module back then. We were originally going to present it back in December before the bomb cyclone hit, and this got rescheduled. And I'm just trying to remember. It seems like
That'd be the summit.
the summit. June. Thank you.
Okay.
Yeah, because that was like 6 lifetimes and an election ago, and I can't remember further back than that. Anyways, so we're going to give a status update on where we are on that. And what we're going to do is I'm going to talk for a few minutes, and then Yair is going to talk for a lot more minutes. And this is the agenda. We're basically going to describe the module, the interface to it, and then Yair is going to talk some more about the internals on it, and wrap up with some futures, things that we're working on. So, what we talked about back in June, thank you, Madeline, for remembering that, was both AWS and Google had implementations of vector search that were brought to market. And, after the relicensing event, we decided that, the project needs a vector search module. And both companies put their hands up and said, take ours. Well, the management said, you guys go off and figure out how to merge these two together and take the best of the best. And we spent, 5 minutes before we figured out that was never going to work. So we spent quite a bit of time evaluating the code base, and we agreed that the Google code base is the one that should be contributed into Valkey. And that's what the work that's been going on over the last few months is going to culminate on that shortly. Okay. And in fact, today there actually is a search repo up under the Valkey repo. It's private right now, but I think it'll be going public any day now.
Yeah, I
And,
think just after
we have
this
a few,
meeting.
yeah, I think we have a few more I's to dot, et cetera. But you should expect to see that repo out there with some tooling so that people can use it. Basically, now in the larger sense. Okay, and we're both working on improving that considerably. There's some futures at the end. We'll talk about, describe the kind of work that's going on it. But I'm going to spend a couple of minutes and talk about what we have today and what it does. And then, like I said, Yair will talk about what's going on under the hood. Okay. So the work that we've done is essentially a subset of the Redis search module itself. The commands that we've implemented are a subset of the Redis search. We've taken the view that there is a fair number of people out there today that have built applications using Redis search. And we'd like those people to be able to move over to Valkey painlessly, and maybe even send some money to one of the two of us or some other people too. That do get paid. It is a business after all. So the commands that we have are a subset of the Redis search. We maintain the same semantics. Our philosophy is, if we're going to do something, and the way that Redis search did it works, then we should do it the same way. There are a few places where we think maybe it didn't quite work right. We reserve the right to, as a group, figure out that we want to change that. There are some places where I think there are, some additions are useful. You'll see that. But in general, having fidelity to Redis search avoids just a lot of squabbling that doesn't really get you anywhere. Okay, we can all argue that we don't like the syntax, or we don't like this or like that, but it's like the old wars with editors. Who's got the best editor? Well, it's the one I'm using right now. They're all bad. I think that's really true here also. So semantically, with the search module, you create indexes. Okay, you can create any number of indexes that you want. There's a separate namespace for the indexes, and the indexes are global. In a sharded system, the index covers the entire cluster. Okay, so this is a little bit reminiscent of some of the discussions that we had earlier about maintaining the illusion that the cluster is one unified set of data. So that when you do a query operation, the entire cluster gets queried. Okay. So when you create an index, it has a bunch of fields in it. You define the fields, and each field has a certain type. So in that sense, it's very reminiscent of a SQL table. A Redis search index and a SQL table are sort of conceptually the same thing. You define the fields, and the rows of your table are individual Redis keys. Okay. And the implementation is that you can have hash keys or JSON keys as members of the index. Okay. So once the index is created and it gets populated, you actually don't have to manage it yourself. Once you create the index, the system automatically updates the data when you modify a key. So for example, if you create an index on a bunch of hash keys and you change a hash key, the index automatically gets updated. So in that sense, the index is transparent to you once you've created it. There are no update my index commands. You create the index, it's automatically updated, and then there are commands that you issue queries against it. Okay. I mentioned that there are different types of fields. Today, there are essentially 3 types of fields. You can have a vector field, you can have a numeric field, and a tag field. And a tag field is just a bunch of strings. And there you have the ability to construct a query using values for the different fields. You can construct, for a vector field, we support the KNN search. And for numeric, you can do a range search on that. Or for tags, you can look for specific tag matches. Okay. And you can combine those. So you can say, please go search the vector field, but only look at vectors where this other field is in a certain numeric range or where this other field has a certain value. So for example, if you were doing like an RAG application where you have a bunch of documents that you've created vectors for, you could tag them with, say, the source language. And then you could do a query to say, find me the chunks, the documents that are near this vector, but I only want to see the documents that are in German, or just the ones that are in German and Danish. Okay, so that combined capability is referred to as a hybrid query, and that's natively supported. So I don't know. I don't think there's much value in going through the details of the syntax here. And I think that we publish this stuff afterwards, right? Okay, and it's in the documentation. So there's a lot of good examples here. I think that's probably more worth going into. Here, this is a KNN search for 10 elements, so K equals 10. We're looking through in the my index, but the field is the @embedding field. So you can have 3 or 4 vector fields in the same index if you want. Typically, you do only one, but I've seen occasions where individual records get tagged with multiple vectors. And in this case, this $blob is how you specify the vector. This is the actual vector that we're looking for. It gets encoded in binary, it's 32-bit floating point. And then this says, of those 10, what I want you to do is to return the price and the score. So the system will go out, find the 10 keys where the embedding field is the closest to that reference vector. And it will return those 10 keys, including the price and the score field associated with that. And you can change the fields that you get back. You can say none, just give me the key names. You can get the whole key back. There's a lot of flexibility there. This is an example of a hybrid query. Here, what we've added is to say, I only want you to search through vectors in the embedding where the price field in the same key is in the range of 10 to 20. And there's half open and open intervals and closed intervals and infinities. You can do less than and greater than, all the usual stuff that you'd want to do on a numeric field. And you can actually combine those. I don't know if we have an example of that here. Nope. Yeah. Okay. So you could do price between 10 and 20 that are in Danish. Okay. Those kind of combinations. That's all natively built in. Okay. Other commands, drop my index. You can do an info command. It'll just give you some stats about what's in the index, etc. List will list your indexes. I'll turn it over to you.
Thank you, Alan. All right. So in this part, I'm going to talk a little bit about the architecture. Obviously, the architecture itself has a lot of nuances and a lot of depths on different topics. I would try to cover more the breadth of it and touch the main aspect. Tomorrow, we are planning to have a dedicated session, kind of a mini sub meetup specifically about the vector search. And so if anyone wants, he can also join. And in this session, we will have much more time to discuss the architecture and dive into specific details. Okay, so very high level diagram of the architecture. So we have on the right the valkey search module. We have on the left we have the valkey dictionary. The module itself get notification on mutation that is happening on the key space, on the engine key space by subscribing to key space notification events. Once a mutation is happening, one can issue, for instance, HSET to trigger such mutation. A key space notification event is captured, and the module itself evaluates the mutation. It basically checks the key itself, whether it was originated from a data type, either JSON or hash. And it also qualifies the key itself based on the indexes prefix which was set in the ft create expression. For those that per index that match the index as a key, we basically process the mutation. We fetch the relevant field from the dictionary, and then we process it. The processing is basically done through worker threads. This allows us to scale pretty linearly in terms of the ability to ingest mutations. If we look at the search flow, then we are also leveraging worker threads in order to scale up the search. It is important to note that both mutation and search in the space of vector consume a lot of CPU. It involves creating a graph, and basically we're using the HNSW algorithm, and a vector could have dimension cardinality of high number. And comparing high cardinality vectors, it is CPU intensive. With this simple design, we are able to scale up pretty linearly with a amount of CPU cores. So let's zoom in a little bit more into the ingestion flow. Um, uh, we incorporated an engine enhancement to allow us to synchronously ingest the mutation. Currently, it is this patch is still not yet in the valkey repo, but we are planning to introduce it. This allows the user that is issuing the mutation, like calling the hset command, to have a synchronous interface, meaning that once the hset command is done, also the indexes are being updated with relevant information. As I mentioned, we support two data types, hash and JSONs. We talk about the near linear scale. Once an index is created, we issue what is called a backfill process. And in this backfill process, the intention is to backfill the indexes with the already existing keys in the key space. The way that it is implemented is that there is a task that basically traverses the entire key space and introduce all the keys to the indexes. And there is a throttling mechanism to make sure that we do not consume too much resources while we are backfilling. We also support multi-exec and honors the semantics of the multi-exec. With multi-exec, the multi-exec execution, in order to maintain the semantics, the way that it is implemented is basically we are stopping during the ingestion, we are stopping we are not allowing any reads, and there is just a single thread that is processing the multi-exec. Obviously, this is not optimal in its impact performance, but in order to still honor the semantics of the multi-exec or transaction, basically this is the only options that we had. Looking at search, in order to efficiently execute hybrid queries, we introduced some kind of a layer that we call a planner. The planner basically decide which route to execute the hybrid query. There are two options. One of them is what we call pre-filter, and the second one is inline. With pre-filter, basically what it means that we pre-filter the result set based on the filter, and then we do a brute force vector search on the subset of the vectors. With the inline filter, the way that it's being executed is that while we traverse the HNSW graph, we evaluate each node before we add it to the qualified result, whether it matches the filter or not. If not, then we do not add it, and we move on with the HNSW graph traversal. There is a logic which allows us to determine what is the best route or the least expensive route to execute the query. It involves the amount of entries that qualified for the filter. If it is below some threshold, then sorry, below some percentage of the total index, then we go with the pre-filter. If it is more, then we prefer the inline. And we already discussed the scale up. Maybe just on this note, we also allow scale out of the search. This can be achieved with replica by allowing the replica read from the replica, basically. We support RDB snapshot. We support both diskless and persistent. Diskless refer to the RDB snapshot, which is created to satisfy the full sync, and persistent the opposite to disk. In both cases, we include in the snapshot the indexes metadata and also the index themselves. It is important to understand that creating the graph consumes a lot of resources and time. And we don't want to be in a situation that a replica become a primary and now it's take a lot of time for it to build up its indexes. We also support clusters, and the cluster is the account implementation. The primary use case is to scale out the key space. But with account implementations, it doesn't allow scaling out of the compute or the search. Mainly because the way that it is implemented is that queries are being fed out to the entire cluster. This is because valkey semantics of positioning entries are based on client sharding, which is based on a hash rather than vector similarity. And therefore, once a query or keys are basically distributed randomly across the cluster, in order to run the vector search, we fan out the query to the entire shards, and then we merge the results doing a brute force search on the results to bring the best results. In clusters, index are basically a cluster entity. It is populated throughout the cluster. So once FT create is issue, the index metadata is being populated to all the cluster shards immediately. We leverage the cluster bus for the initial communication. And we also have a mechanism, we are also issuing a verification that every node is indeed having a synchronized up-to-date version of the indexes by periodically sending fingerprints of the metadata. We also support the conflict resolution, and in which cases the conflict resolution allow us a guarantee that we would end up in a consistent state, such that not two nodes that are doing independently conflict resolution might end up in a decision how to address the conflict differently, and we would end up in an inconsistent state. In terms of memory efficiency, as you can imagine, the vector search or vector store space, it's consuming a lot of memory, especially with regard to the memory allocation related to vectors, but also it's having multiple indexes. Is it basically store some information, duplicate some information from the engine of the key space? It also consumes a lot of memory. And we leveraged two main techniques in order to address or mitigate this overhead. One is that we've introduced an engine enhancement in order to share memory between the module and the engine. We still haven't published this enhancement, but we are planning to work with the TSC and the community to publish such. The second technique is what is called string interning. For those who are not familiar, it's basically a design pattern that allows you to avoid memory duplication of strings. And this is applicable especially in the case that multiple indexes could be indexing the same key, and therefore eventually we are ending up spending memory per index per key. And string interning allows to efficiently address this situation. So performance, unfortunately, I cannot really share here official benchmarks yet, but I can share that in terms of performance, if you compare it to Ready Search, right? Ready Search is way behind what the performance that we managed to achieve, mainly because it does not scale up at all. And I cannot share internal benchmarks at Google, but across all the services that are providing vector search at Google, which there are quite of some, memory store is leading the pack in terms of performance. Looking at the future, there are a bunch of things that we would like to prioritize working on. So searchable text field, this is going to be definitely useful, and we have seen a lot of already customers that are actually interested in having such capabilities. Non-vector queries today, it's every the queries that one can run are only in the context of vector with additional filters, but you cannot use the additional field types independently, such that you don't want to do a vector search. You just want to run a query that give you, for instance, a range query on a particular numeric field between some range. So having those, having the ability to run it independently to vector is important. Linking integration, FT aggregate. I think it's kind of you can look at it as similar to group by. The ability to aggregate and run computation on the result. Vector range, addition, aliasing, FT alias will allow us to alias indexes, profile for debugging, and explain as well. Questions?
I have a question about the ingestion. So you mentioned that synchronous ingestion, but also there's a writer thread pool. So the indexing is actually performed by, is processed by the thread pool, right?
Right.
How do you ensure that thread pool contains background threads? How do we
Right.
ensure that it's still synchronous? Also, what's the relationship between that thread pool and the main thread, the Harkrishn main thread?
Right. Yeah. Yeah. So the main thread basically is responsible for mainly receiving the command themselves. Like FT search, we do the parsing on the main thread, but once we finish doing the parsing, then we hand it off to the worker thread. In terms of if we look at the ingestion flow specifically, then I think that your question is more around how do we maintain order such that consuming from a worker queue by worker threads might lead to a situation that mutation are being processed out of order, and you eventually reach a situation that your index does not reflect the most up-to-date data in the dictionary. So we address this by having the specific, a special data structure that allows you to have maintain order per key. So on every mutation that is happening, we record the key, and consecutive mutations on the same key would end up in a queue, as an entry within a queue of a particular key. The worker thread is responsible for consuming an entry as a whole with the entire mutations that could be happening, and it would process it in order as a of the queue itself.
For example, if one client has the issues 10 hsets commands followed by one ft.search.
Right.
So each of those hset, those key will trigger a key space event and then put a mutation in the writer in the queue, right? The
Right.
queue.
Right.
But the ft search command will be put in the reader.
Right. But we have a single, so we block the client. So every hset command that you've been sent, the client is blocked until it is being processed by the index. So effectively, all these 10 hset command issued by the same client would be processed kind of serialized in a sequence order. Like the first one, the client would get notification that the first hset is being processed, and it would issue the second one, and so forth.
When the ft search is processed,
if it is on the same connection, it is already guarantees that all the hset command are already processed. If it is on a different connection, there is no guarantee.
but they are processed by the thread pool.
Right.
So how do you?
But we block the client. We block the client that issues the hset command until the worker thread managed to process the item which was added, the task that was added to its worker queue.
Maybe you can explain how the module blocks the hset response from being sent. What's the interaction the other way around? It's the response which is not sent to the client, it's heading up the server side.
Right, right. Yeah, so once the client issue exit command, right? Exit command arrived to the engine itself, and then there is a key specs notification that is caught by the model. The model is also blocking the client. Now the worker thread will consume the task itself, process it. Once it is done, then it's actually release the client.
Like across clients, you don't run the same queries or sets on the same data. They have to run exclusively. So what you're saying, like you can't have a set and a query running at the same time on the same data.
On the same connection, you mean?
Cross connections. Can they run
You can,
concurrently?
yeah, you can.
Okay.
Right.
You can issue them.
Yeah, you
They
can issue
won't
them.
execute
Okay. but you're gonna-
simultaneously
they won't
under the
execute
hood.
Yeah,
Under the
But you don't
hood.
see that.
right.
But from their perspective, they're
From-
blocked.
From the user's perspective, the locking is just a performance of latency.
Yeah, they're gonna see it. They didn't see it.
Correct. But
So
but
But you would anyway.
anyway, like if you run, like if a specific client is opening two connections and it is issuing one command into one connection and then another command in a different connection, there is no guarantee that the command would arrive to the server in the same order that it was issued.
yeah, but like what if you have one client doing an H set and another, I don't know how expensive these queries get. I'm not familiar with the search module. Can they get into the seconds or if they do something really crazy or?
It's not in the seconds.
It
It
doesn't
is
get that
more,
high.
it is
Okay.
more in the low
Okay,
milliseconds.
so you can still have like an expensive query and an H set gets stuck behind it. That's a possibility.
Right, but stuck is in the typically millisecond, tens of milliseconds.
Yeah, yeah, yeah. I don't know how crazy these queries can get. so-
Well, I mean, there actually are pathological cases where it could get really large, but you got to kind of work to do that.
Yeah.
So.
Yeah,
I
but there is
understand-
not such thing as stuck, right? It is,
Yeah.
it is really, it's like, what is the expectation of when it should be processed as
Yeah, you see
the
some
command.
latency on the response, I'm assuming, right?
but there is no guarantee that like two commands that have been issued by the same client would be even may arrive at the same time on this to the server.
That's true, got nothing to do with the server.
Right. Yeah,
But
it's-
you can issue two commands on two different clients from the same application. There's no guarantee what order they're going to
Yeah.
execute.
Sure, but
Whether they're reads or writes or whatever.
It-
This is no different.
your
Right.
first client can be stalled behind the query of the second client. I don't think the queries are that
They
expensive.
don't stall each other. It's
They
just on
don't.
the same connection, you would get stalled, right?
Okay,
So it's like connection one, H set,
oh,
H set,
so
search,
cross
right?
connections, you don't. block.
Yeah, the
You
other
don't.
one, so the
Well-
main thread is completely freed after it gets to the background thread, right? So
so we
There's
block the
blocking
client.
between reads and writes.
Right.
When it says it's time to do reading, everybody does reading.
So the one client's writing.
But if one client is writing, then all the reads are held until that writing.
Right. What if there's a ongoing read? Do you block the writes until the read
The
finishes?
writes have
Yeah.
to- Yes.
Yeah.
Those are two different connections.
but yes, I think this
Yes.
is actually a different, you didn't talk about it, but the read write exclusion, right?
Right, yes. Yes, it is a different topic is that we haven't covered here about how do we maintain consistency across indexes. It is a kind of very interesting and also complex domain. A lot of database use, like for instance, MVCC, or there's different techniques. We opted into a model which we basically timeshare between split the CPU between read and write. It works better for in-memory and databases, and at least and it also allows you to have a lock-free algorithm for the read pass, because once you're in a read, it is guaranteed that there is no one actually mutating the data. And therefore, one of the issues with MVCC is that on a multi-threaded environment, it could be that a single thread is now mutating some data structure, and read is happening. The read would have to wait. And this contention, this situation would lead to a degraded performance. In our case, our synchronization is very limited. It is confined to just synchronizing between the reads and write. Obviously, writing on the same data structure, there are additional synchronization, but the read pass become lock-free.
I think just a quick time check. I think we wanted to get another session in before 7. So I think you guys could continue either tomorrow or just after.
Sure. Thank you, guys.
There as well. It's time because I was gonna say it's like just develop a preview. Like, see, developers can play with it and get.
Hey everyone, I'm Karthik. I'm a valkey contributor and a software engineer at AWS. This is a presentation on Bloom filters for valkey. Just for a quick overview, we'll first talk about Bloom filters, some use cases, and we'll introduce valkey-bloom, what it is and what it supports, and then we can go more into the internals of how it works underneath, and talk about scaling, non-scaling, and then some example usage of this. For a quick overview, Bloom filters are a space-efficient probabilistic data structure. So you can use this to add items, and then you can check whether they exist or not with a configured false positive rate. So false positives are possible, but false negatives are not possible. And the part here which makes it space efficient is with these add operations, you're not actually allocating the items. You're really underneath the add and check operations, you're performing bit set and bit check operations, which makes it more space efficient once you have the bit vector created. Some use cases for this include reducing lookups to backend servers and databases. And fraud detection can be used in examples like keeping track of locations and seeing if a transaction is being made from a unknown location. And in recommendation systems, you can use it for checking whether you've previously recommended this advertisement or not to a user. And you can get similar set and check functionality if you're inserting items into sorted sets and hash maps, but this would require higher memory usage. And you can get similar bit operations through the bit op command. There are some libraries that are built around this, but the advantage with Bloom filters would be that you can get a single valkey command that would execute all of these bit operations through a single command. And yes, you can get better performance with Bloom filters to do some of this. So yeah, this brings valkey-bloom, which we built as a open source Rust module. It's a valkey module in the valkey.io project that's API compatible with the API syntax of Bloom filters from other libraries, rebloom based syntax. And this is already supported by several client libraries, including Redis by Node-Redis. We support scaling and non-scaling of scalable Bloom filters and persistent modes, including RDB and AOF, so that you can have a Bloom object, add items to it, and restore the same state later on. And other standard data type operations, including copy, debug, and active defrag, can be performed on the Bloom filter data types. You can also use the existing API, so the Bloom filter commands that you customize the Bloom object that you're creating, so you can choose specific capacity, expansion rate, false positive rate, and you can control whether it's scaling or non-scaling. And we'll talk more about some of these in the next slide. So yeah, before going more into how our structure looks, we can just talk about the Bloom filter first. So the main things that you would use to create a Bloom filter are a capacity and a false positive rate. So the capacity is how many items you want to store on this Bloom filter. And the false positive rate will be something like 0.001, which means 1 in every 1,000 operations will be a false positive. So even though I might not have inserted something in it, uh, there is a false positive that can happen, which would return that it does exist. And you can choose a very strict false positive rate based on your use case to kind of mitigate this. So once you have a false positive and a capacity, you compute a number of bits. And with this number, you create a bit vector. What we've done, we use a zeroed out allocation, which becomes a lot more performant for large bit vectors. So you have an entirely zeroed out allocation, so it's lazily, so you have the benefit of lazy allocation here. And then you have hash functions that get created. So based on the false positive rate, we have a certain number of hash functions. Usually libraries use something like dual hashing. This is what is used by us. We just have 2 hash functions, and if we compute that, we actually need 7 hash functions. We just synthetically compute the remaining hash functions from this. And then, yeah, the seed is something that you can use to recreate the same deterministic behavior of that Bloom filter. So this is what we use, and we save some of these informations when you're taking an RDB save, for example. So the way it would work is when you want to add an item to a Bloom filter, you would run the item through the hash functions and set the corresponding bits to 1. And to check whether it exists, you would run an item through the hash functions. And then if all the indexes return 1, then you know that there's you can say that the item exists with a false positive rate percentage. And if any of them return 0, then the item does not exist. So we build Bloom filters. We have a Bloom object that essentially can act as a scaling or non-scaling Bloom filter. And a non-scaling Bloom filter is, for most part, just a wrapper on a Bloom filter. So we're using an external Rust crate that provides this raw Bloom filter capability, and we've wrapped around this. So you just provide a false positive rate and a capacity. And in this case, if the capacity is 100, you can add 100 items to this. And when I add another item that gets detected as a new item, that item add would fail. It would get rejected, saying that it's already reached its capacity. So the difference with a scaling Bloom object is it would start out the same. You just have a single Bloom filter. But then once I add 100 items, if I add another item, it's going to scale out. And then the second Bloom filter gets added to the vector of Bloom filters within the same Bloom object. And the second Bloom filter will have a capacity which is X times the previous Bloom filter. So here in this example, the expansion rate is 2. So 2 times 100 is 200. So I have a capacity for 200 within this Bloom filter. And yeah, and it continues. If I add 200, the 201 item add would trigger another scale up. So you have the third that gets added. So with this, you can continue to go on scaling your Bloom filter. Another property which is specific to scalable Bloom filters is the tightening ratio. So when you have a tightening ratio, we use this to maintain the overall false positive rate of the entire Bloom object. What this means is if I create a Bloom object with a false positive rate of 0.001, every new filter that gets added while I scale out has a stricter false positive rate. And this keeps it bound closer to what they had requested upon creation of the Bloom object. Okay, yes, so this is more of the API syntax itself. at the top. So this is a non-scaling example. The BF reserve command can be used to create a non-scale. So that's just the name of the filter. I'm calling it non-scaling filter. 0.001 is a false positive rate. 4 is the capacity, and I can specify that it's non-scaling. And once I add 4 items to it, if I add the 5th item, it's going to fail, saying that the filter is full. And you can use the bf.info command here. You can also use bf exists. After it reaches its capacity at this point, you can only use it for reads. So I can just use it to check whether I've added something to it. But beyond that, you can't use it for adding any more items. And you can see that the expansion rate is nil, and that the number of items inserted matches the capacity. Yeah, and this is an example of a scaling filter where I can use the same command, the bf reserve command, and then the filter name, the false positive, and here the capacity is 1, and the expansion rate is 2. So with this, we have a scaling filter where I can add 1 item, and then here we've already reached the capacity. So if I add a second item, it would trigger a scale out. And we can see that here that the number of filters is 2, and then the overall capacity is 3 because the second filter was is 2 times the first one. So this is mainly the 2 modes that are supported for Bloom filters: scaling and non-scaling. And through scaling, you can essentially reach higher capacity. You don't need to have a single bit vector that's created at the very beginning. That's too large. If you think that you want to start with a smaller capacity, you can use that, and then it would scale out, and you'd essentially be able to add more items as you keep the Bloom object and keep populating it. From numbers we've computed, you can reach over hundreds of millions of items that can be added to Bloom objects with the memory limits that we enforce on them. Just as a summary, this is an open source module we built to bring a Bloom filter support to valkey. It's API compatible with existing client libraries, and we're working towards the first valkey-bloom release, as well as probably more discussions with the core team about release and bundling of modules with the core. This is a project that we have built in open source from the start. Through an RFC process. So there were several people who helped review this, and several people who have contributed to the project as well. So thank you to all the contributors here. Any questions? And
Yeah, I was just wondering, is there any way it differs from like existing Bloom filter modules? Like, is the info the same, or a little bit different?
That's a good question. So we've built it so that it's a superset. For most part, it is exactly the same, except there is one command which we have expanded beyond. There are things that are different for sure. I can, for example, one thing we support is you can either, this has configurations. So we have configurations for different modes. You can use a random seed mode or a fixed seed mode. So if I want every single Bloom object to have the same deterministic behavior, I can use that configuration. We have a memory limit that we enforce for more stability in terms of operations like persistence. This is a configuration as well. By default, we set it to 128 MB. And the reason was, it's both, just looking at RDB save operations and other aspects, it works pretty well. You can also reach 100 million items within a single object with this limit. And if you need more, you can change the configuration. There are, with the command, there is one command called the bf insert command. So we've extended that. So it's a superset where you can provide a seed and a tightening ratio as well. And some of these things don't exist in the other modules. Like you can't configure some of these things like a tightening ratio or a seed or capacity. These configurations don't exist. I think key space events is also another thing that might not be here in other modules. ACL as well. Like there's an ACL category that we've added.
I remember there is issue about active defrag. That issue resolved, and what solution did we end up with?
Yeah, so with active refrag, we actually went ahead with implementing a solution within the module itself. So without any code changes, we have been able to defrag every single allocation within a Bloom object. So we actually use we actually take advantage of pretty much every module API with defrag. We start with the loop of the Bloom filters. So you saw that there was a vector of Bloom filters within a Bloom object, and we loop through that. We defrag each allocation, and then we also use a timer. There's an API which says, should I yield? Yeah, if it's taking too long, we essentially yield back to the main thread. We also use cursors, so you can defrag in iterations through this, and then you can pick back where you left off on the same object, the next iteration. And yes, so with this, we found a way to maintain pointers to the actual allocations, and with that, we're able to actually defrag it.
I'm thinking about we are probably the same thing for JSON.
Okay, yeah, I think it should be possible. Yeah, we can talk more about that. And the code for this is in open source. Cameron worked on that part, so you can.
Are you using a special limit allocator?
No, we're using the valkey allocator. So on startup, we use the valkey allocator, and then, yeah, it essentially goes through that. We extended. Yes, so yeah, it supports. So this is built in Rust. So in Rust, you have the allocator, like a global allocator, which has alloc, dealloc. We extended it to have alloc zeroed as well to help with large allocations where you want a zeroed out allocation.
Actually a feature.
Yes, yeah. There's, yeah.
Easily documented.
Yeah.
The idea to the approach.
Yeah.
I think you mentioned before testing.
Yes, yeah. That's another thing that we've added within this. So we wanted to make sure that every aspect of this was tested against servers. So we have a Python lightweight framework that we've written here that we're going to work on open sourcing. Yeah, so that's something that we use for testing.
Yeah.
And, yeah.
Should share it because I think for research, some
Okay. Yeah.
Yeah, we should share notes.
Yeah. That sounds good. Yeah.
Do you do any comparison, like compatibility testing? Compare outputs between this and like Redis Bloom or something? Or is that just
we do compatibility testing with one client. So in our framework, we use Python and we use valkey-py because that's available. So they actually have Bloom filter commands that they have wrappers around first. So we test that we're compatible with that. We don't use their library. We don't pull their library or anything. Yeah. Yeah, we did run perf tests and we saw that they were essentially comparable in numbers. Of course, it probably depends on where you are running this. For example, if I ran, if you're running this on Valkey, we'll also get the benefits of Valkey itself compared to Rebloom on their servers. But even keeping the same server, we had roughly on par for scaling, for non-scaling, scaling. And yeah.
I guess this is your question. Like the reason we implemented is a module on a support data structure.
Yeah, we were, so, yeah, we, so,
Like you said, the armory.
okay, yeah, yeah,
Yeah, I took that back quickly.
okay. Yeah, so yeah, we did talk about this for some time, and there are benefits to having it separated out. You can take advantage of existing libraries that are out there in Rust. I think like there are memory safety advantages. There's a few different sets of advantages to having it separate. Uh, yeah, so yeah, this was something that we did discuss before, and as well as part of the RFC as well. This was something that was brought up and talked about.
Let's talk about how like we know that the community needs modules, like we don't want VSS.
Yeah.
Like that's definitely too big. And so then there's some spectrum between what goes in the core.
I don't know how to draw that line. That's why I was curious. Like, what we're doing.
Yeah, we talked about it a bit with both JSON and.
Feels core, but not even this fine.
Really, if there's a type of the core itself doesn't. Module interface is something else, a good way to maintain code separately so that it easily maintained. What did you think?
Or like you mentioned AOF rewrite and RDB, like is it also using the AOF block, like the AOF rewrite needs to also down copy AOF?
Yes. So what AOF rewrite does is we instead of so we kind of optimize here where we have a command that gets written into the AOF called bf.load, and with that we have so instead of having so AOF rewrite would be called when you're trying to truncate the AOF, and we have a command that can recreate that entire state of the Bloom object, and that's bf.load, which has a serialized format of the Bloom object.
But does it also log as you are adding items to the?
I mean, yes, like the regular commands would until it gets truncated, and in which case this would get written instead. Yeah, so yeah, the same time when you're replicating, it will go to both places.
So it's really just storing the good vector, I think.
Oh yeah, yeah. For most part, that's what the serialized data would contain. Yeah, and that as well, like the seeds for hash functions, the properties of it, and yeah. Okay. Yeah. All right. Yeah. Thanks, everyone. There's no other questions.
Just want to say thank you, Google.